All right, folks, let's go ahead and get started with today's topic. So what I want to do today is to build into what we call the Bohr model of the atom. Which is sort of our first elementary sort of quantum mechanical model of the atom, which was developed very early in the 20th century. It's developed by a scientist by the name of Niels Bohr. And the way he did it was to look at how light interacted with atoms of a given element. All right, so we'll talk more about the experiment just a little bit later. But I just want to touch on a couple things here from the video just to clarify. So in the video, we discussed the two ways in which we can look at light. And we said there are two ways to model light. One was to model light as a wave. We can say that light has wave-like particles. And the other option was to model light as a particle. All right, so kind of which way we want to do this depends upon the model that we're trying to develop for the atom. Okay, so we're going to find out in the Bohr model, it works out a little bit better to think about light in terms of the particle model. Okay, and the particle model is what we really focused on in the video. Okay, so the particle of light is known as a photon, which you guys remember from the video. And we can talk about the energy of a photon. We know that it's equal to h, which is Planck's constant, times nu. So that's a constant, that's 6.626 times 10 to the minus 34th joule seconds. Okay, and nu here is the frequency of the light. We'll get to that in just a second. Okay, so frequency really, when we talk about it, comes from the wave model of the light. So I want to talk a little bit more about the wave model. We kind of touched on it in the video, but I want to make sure that we're all on the same page about it. So what we're doing here is we're assuming that light is going to behave like a wave, just kind of like a wave in the ocean or at the beach. So the idea is if you think about a wave in that sort of context, the wave propagates or moves in a certain direction. So I can sort of look at a wave, if we're looking at it sort of side on, as like a sine wave or a cosine wave moving through space or through the ocean or whatever we want to think of it as. Okay, so the wave is propagating or moving. Now, it's moving at a given velocity. Now, normally what we do is we think about the velocity of light, for example, in a vacuum. All right, and light can actually slow down a little bit when it's actually in a non-vacuum environment. But we usually actually use our benchmark velocity of light as the speed of light, and that's how fast light moves or propagates in a vacuum or in space if you want. Okay, and that's given by a constant c. That's the speed of light, which I think we did define in the video. And that's going to have a value of 3.0 times 10 to the 8th meters per second. So notice that's a velocity or a speed. Okay, so we can think of the wave as moving through space at that speed. Now, there are a few other ways we can characterize the wave. Another way to characterize it is the distance or length between two peaks. Okay, so that we call lambda. And lambda showed up in the video last night. And lambda turns out to be the wavelength of the light. Could also be the valley to valley distance, whichever way you want to think about it. So it's got to have distance or length units. So we might find wavelengths in meters or maybe nanometers or micrometers or something like that, depending upon whether it's long wavelength light or short wavelength light that we're talking about. Okay, but either which way, it has to be a distance or length unit. And then there's the other thing that we just sort of talked about in the particle model, which is frequency, and that's nu. And what frequency is if you were standing in one place, okay, and you were counting the number of peaks that pass by you as the light propagates past you per unit time, that would be the frequency. So it would be the number of cycles or peaks that you see per unit time passing by you. Okay, so frequency is always going to be given in terms of, for example, cycles. Think of a cycle as being peaks per second. Now, a cycle really isn't a thing, it's an event, right? So another way to think about this is inverse seconds or events per second. And another term for that is the hertz, Hz. So a hertz is just an inverse second or things happening per unit time, okay? So in other words, peaks passing me per second. All right, so that's what frequency happens to be. So if you actually compare two waves of light, so I could have a wave of light that looks something like this, okay, propagating at the speed of light. So they both move at the same rate. And then you compare it to something that looks like this. Okay, you can kind of see that even though they're moving at the same rate or at the same velocity, okay, the wavelengths are different. So you'll notice that in this case, the wavelength here is a much bigger value. So lambda 1 is there. And then the wavelength of light for my second type of light would be lambda 2. And you can see there that lambda 1 is obviously greater than lambda 2. So light can have different wavelengths associated with it. Now, does the wavelength affect the frequency? Well, yes, it does. Because as you move the peaks closer together, for example, in the case of lambda 2, you're going to see more peaks passing you per given time because light is actually propagating at the same speed, regardless of the wavelength. All right. So what ends up happening here is that we see two different frequencies. And in this case, what we'll see is nu2, which is frequency associated with lambda 2, is going to actually be greater than nu1. So what this shows you is that frequency and wavelength are inversely proportional to each other. So in other words, as the wavelength gets bigger, the frequency gets smaller. And you can actually see that in that drawing there. Okay, so here's the relationship, which we actually showed in the video. We can say that nu, which is equal to frequency, or is the frequency, is equal to a proportionality constant, which is the speed of light, because that's the thing that's common to both of these, times 1 over lambda. And oftentimes we write this as just c divided by lambda. Okay, so that shows that inverse relationship between the two things. In other words, as frequency gets bigger, wavelength gets smaller. All right, so that's an important thing to remember. And we also know, if we want to go back to the photon model, and we showed this relationship in the video as well, we can say that E is equal to h nu, and then we can just substitute nu is equal to c over lambda and get energy in terms of wavelength. So we can say hc divided by lambda. Okay, so what we notice here is that the energy of the light is proportional to frequency, but inversely proportional to wavelength. So as the wavelength gets bigger, the energy of the photon of light gets smaller. All right, so those are kind of our key relationships that we need to remember when we think about this. Okay, so that's kind of just summarizing some of the stuff that we did in the video last time. And I just wanted to make sure we're all on the same page about that. Everybody okay with that? All right, so the next thing that we kind of have to think about is this thing called the electromagnetic spectrum, which is where we talk about different types of light or energy. All right, so in this case, we can think about all the different kinds of radiation that we have. Now, radiation is just a fancy term for light. Okay, so we have all different kinds of light of different wavelengths, frequencies, and energies. Okay, so if we talk about in terms of energy, all right, which ones have the highest energy? Well, it turns out it's the really short wavelength, high frequency light. So at the really high energy end of the spectrum, we could have things like X-rays. Okay, so X-rays are just a type of light. We can't see it, but we kind of sort of know what it does, right? It penetrates into soft tissue, for example. So we think of X-rays as being penetrating radiation. Now, as we move to lower energy, we can get to UV or ultraviolet light. So that's part of the kind of light that's given off by the sun, which gets absorbed by our skin and gives us a sunburn, right? So that's UV light. So it's somewhat penetrating. It can actually affect your DNA and give you skin cancer. So it's kind of high energy too. Then when we go to a little bit lower energy light, we get to the visible part of the spectrum, which is the part we can see. Okay, so that's your rainbow. Okay, that's the white light we usually talk about that comes from the sun or from a light bulb that we can then divide into the various colors that we see, Roy G. Biv, right? Your rainbow. And then if we go to even lower energy light, we get to infrared. This is thermal radiation, so that's heat that you can feel. And then we could even go further than that and go out to things like microwaves or radio waves. Okay, microwave radiation, as you know, we can use to heat up our food. And we also can use it for communications. Okay, so if you've heard of a CB radio, that's on the microwave band. So we can actually use that as a means of communication. The same is true with radio waves, which lie at even lower energies. Okay, so again, let's kind of focus on what we're talking about. As I said, X-rays tend to be the highest energy. And the microwaves over here tend to be the lowest energy. Okay, so what does that tell us? Well, it tells us in terms of frequency, the highest energy have to have the largest frequency, right? So low energy light has low frequency, smallest frequencies. And then how does wavelength show into that? Oh yeah, wavelength is really small at high energy, large frequency. So these are the smallest wavelengths down here on the X-ray. And then the longest or largest wavelengths are over here on the other end of the spectrum. Okay. Now, as it turns out, we don't have to really worry too much about all these different kinds of electromagnetic radiation. The kinds that we're going to ultimately worry about in this chapter are going to be these two, the ultraviolet and the visible. Okay. And the reason why we worry about these is because they're the ones that interact most readily with atoms. And that's what we're ultimately trying to do. Okay, so we're trying to find out something about atomic structure by shining light on it. So it's the ultraviolet and visible parts of the spectrum that actually cause atoms to do something, okay, that we can actually observe. So that's why we care about those ones. Okay, so in terms of like a wavelength range there, that's going to be about 200 nanometers up to about 800 nanometers roughly. Okay, so that's the wavelength of light we're really talking about here. The visible part of the spectrum is roughly going to be from about 400 nanometers out to about 800 nanometers, with your violet being down around 400 and your reddest red being kind of out around 800. Okay, but that's the general range of radiation we're going to be talking about when we talk about interaction of light with matter in terms of atoms. All right, everybody more or less with me at this point? Everybody good? Okay, so let's talk a little bit about this Bohr model now. We kind of have the tools that we need to discuss it. So let's talk a little bit about the experiment first. So let's say I've got, for example, sunlight. Okay, and we know that the sun radiates all kinds of different wavelengths at us. Okay, it's called a white light source. Now, the idea here is that I could, for example, have a slit here, and I'm going to let some of that sunlight come through the slit. And then what I'm going to do is I'm going to expose it to a prism. You guys ever played with a prism before? I think you guys kind of know what a prism does. If I take light from the sun and I shine it on a prism, what do you get out the other end? What do you see?
A rainbow.
Hey, get the rainbow, exactly. So what it does is it actually through a process called refraction, which is bending of light, and another process called dispersion, it actually gives me all the colors of the rainbow. So you get your red, you get your orange, you get your yellow, G is green, blue, violet, okay? So you get all the different colors of the rainbow out. Now this is actually got a name. It's called a continuous spectrum. And we call it a continuous spectrum because we see all the different colors, and the red blends into the orange, and the orange blends into the yellow, and the yellow blends into the green, right? There's no breaks in it. So that's why we call it a continuous spectrum. All right, so that's what we see if we have a white light source that contains all the different wavelengths of, let's say, ultraviolet and visible light. That's what we would see. All right, now let's do an experiment. Let's have another light source over here, but in this case, we're going to take hydrogen atom. Okay, so that H there represents a hydrogen atom. okay? And I'm going to put that hydrogen atom in an electrical discharge. Usually this is called an electrical discharge tube. And you guys have seen this. Have you ever seen a fluorescent light, for example? What is it? It's basically two electrodes, and we apply a voltage to it, real high voltage between the electrodes. And then you've got gas backfilled in there. What ends up happening now is that the atoms of gas in there feel the effect of that electrical discharge, and they absorb some energy. And then when they absorb energy, guess what? They give off light. Okay, so hydrogen atoms will do exactly the same thing. We could actually put H2 gas in there, but then the electrical discharge actually breaks the bonds between the hydrogens. So you have hydrogen atoms in there. They absorb some of the energy from the discharge and they give off light. Okay, so we can do the very same kind of thing. I can take some light from the hydrogen atom. I can run it through a slit and again, run it through a prism, just like I did before. And now you get a spectrum, but it's not a continuous spectrum anymore, okay? What you're gonna get are individual lines at specific wavelengths. So you get a line at 656 nanometers. You get another line coming out at 486 nanometers. You get another line coming out at 434 nanometers. And then you get a last line. This is just the ones in the visible part of the spectrum, but about 410 nanometers. Okay, so this is called a line spectrum because what you end up getting is darkness between the individual lines that come off at specific wavelengths. So you don't get a nice continuum rainbow anymore. You get individual emission lines at very specific wavelengths. Okay, so this is called a line spectrum. Okay, and that's different from what we get if we have a continuum source like sunlight or say like a light bulb or something like that. So hydrogen is doing something very interesting here. Okay, so what are the observations that we make that we're going to base our model on? Well, first of all, obviously hydrogen atoms absorb energy from the electrical discharge. Okay, and then the second thing that we notice is that the hydrogen atoms give the energy back. But not in the form of electrical discharge, but in the form of light coming off at very specific wavelengths. Now, if you remember what wavelength means, wavelength can be converted to frequency. Oh, and frequency can be converted back to energy, right? So if you think about this, when I say that I've got light coming off at different wavelengths, what I'm really saying is that I've got light coming off of the atom that represents specific energies associated with some event, okay? So that's really what we're saying here. So what's the result of all of this? Well, the overall result that's important to us is that the hydrogen atom, when we get it excited by letting it absorb energy, gives the energy back, but it only gives off specific energies. And that's indicated by the specific wavelengths we get. We could say of photons, because that's how we think about light energy. And we have a name for this. When we talk about only specific energies being given off, we say that the energies are quantized. Okay, so this is what we mean when we talk about a quantum mechanical model. We're saying that only specific energies can be associated with absorption or emission of radiation. Okay, so the atom won't give off a continuum of energies, it only gives off specific energies. And that's a really, really important part of the model. Okay, so everybody more or less clear on what we're seeing and what we're taking out of this? So here's the cool thing. This is what Bohr saw, okay? Now, obviously, he can't see an individual atom. He doesn't have a microscope that lets him go in and see what the atom looks like, right? So the best he can do is take what's known about the atom in the early 20th century, and we have to think about what was known back then about it. Well, we kind of know, if we think back way back to like chapter 2 or something like that, when we talked a little bit about atomic structure, that the atom has a nucleus, right? And what's in the nucleus? Well, in those days, the only thing they knew about were protons, right? And then they also knew there were electrons out there. But remember, the protons were in the center of the atom and the electrons were somewhere on the outside. That's all we really knew up to that point. So what Bohr is trying to come up with is a model that tells us what the electrons are actually doing when we shine light on the atom. Okay, so here's what he came up with. He said, okay, we know there's protons out there. So we're going to put the proton, and we'll just do this in terms of the hydrogen atom, which only has a single proton, right? And the hydrogen atom only has a single electron. And what Bohr says is, okay, that electron's got to live somewhere. And we know it's outside of the nucleus, which is where the proton is. So it's out in the so-called electron cloud. Okay, and that's kind of where we left our model last time. But now Bohr wants to get more specific about it. So Bohr says, okay, we're going to let that electron live in an orbit. Okay, so we can think about sort of a circular orbit around the proton, kind of like a planet orbits around the sun. Okay, so this little semicircle I've drawn here is an orbit. Okay, and I could put that electron, which I'll just represent as a dot here, in that orbit. Now, that's normally where the electron wants to be. Now, Bohr had a good reason to think this might be the case, because what you have to understand is that the planetary model was very, very well understood at this point. Okay, so we had all our theories of classical physics to describe exactly why the planetary model is a good model, right? So it has to do with gravitational attraction and the fact that there's centrifugal force that's pulling in one direction and the gravity's pulling the other direction. And we have rotational inertia and all this other stuff here that's kind of holding everything together, if you will. That was all very well understood. So Bohr said, hey, let's just say that atoms work the same way as planets in the solar system. Seemed like a reasonable thing to do. So here's the deal. Just like we have different planets in our solar system, Bohr said if we had this miniature solar system, I can have other orbits out here. So I'm going to kind of draw some other orbits out here. Now, even though we've only got one little planet in our solar system here, that's that single electron, Bohr said, all right, if a photon of light comes in here and it interacts with the electron, what it could do is it could actually, through collision, pop that electron up to a different orbit, if you will. So in comes a photon, which I'll call h nu. It hits that electron and it pops that electron up to a different orbit. Okay, it's just transfer of energy is all we're talking about. Okay, and then the electron will momentarily hang out up there. Okay, so I could kind of put the electron here. But once that photon gets absorbed, the electron doesn't really want to stay in that other orbit because that other orbit has a higher energy associated with it. And the electron kind of wants to get back to its original energy. So what ends up happening is the electron then comes back down to where it originally was. And because energy has to be conserved, in other words, we can't create it or destroy it, okay, that energy has to be given back off when the electron comes back down. So as a result, a photon comes off. So I'll call that h nu. I'll call the initial photon h nu 1. I'll call this h nu 2. Okay, so when that electron decays back down, a photon of equal energy is given off. Okay, and the energy of that photon, because this first one has to have, this first energy level has to have an E1, the second orbit has to have an E2. Well, the difference has to be the difference between the two, which is E2 minus E1, and that's going to equal the h times nu. Okay, that's the energy of the photon that's given off. Oh, and remember, that's also equal to hc divided by lambda. So now what we have is a wavelength that's characteristic of that energy difference between the two orbits. Okay, so that's what Bohr said was actually happening. All right, so what Bohr did was he gave these different orbits, which he also calls energy levels because each orbit has a different energy. He gives each one a given quantum number. So he said, okay, n is equal to 1 for the first orbit, n equals 2 for the second, n equals 3 for the third, n equals 4 for the fourth, and we can go on outwards from there. All right, so what have we got now? Well, we've got some definitions. As we just said, the n here is the quantum number for a given orbit. And these have to be integer values, starting at 1, 2, 3, and then going upwards as far as we need to go. Okay. Now, he also in his model defined an orbit radius. So that's called an r sub n. This tells us something about the size of the atom, right? And it turns out that r sub n, the orbit radius, is equal to n squared, which is the quantum number, times a constant a naught. Okay, and a naught just has a, it's a size. So basically it's just 53 picometers. Okay, so it's just a constant value of size. So basically what you can see here is that the atom gets bigger, okay, as we move further and further out to larger orbits by the square of n. Okay, so the atom's getting bigger and bigger and bigger if the electron goes to an orbit further and further out. And that kind of makes sense when you think about it. And then the other thing is we have to define that energy associated with a given orbit. Okay, so that's that energy I was talking about up top there. So I'll call that an E sub n. So that's going to be the electron energy associated with a given orbit. Okay, so if an electron is housed in a given orbit, we're going to say it has a certain energy which is characteristic of that orbit. Okay, so we can say that E sub n is going to equal to minus r sub h, that's a constant, divided by n squared, where n is the quantum number again. Okay, and RH, this constant, is called the Rydberg constant. And it has a value of 2.18 times 10 to the minus 18th. And it's an energy thing, so it's got to be in terms of energy units, which are joules, which we remember from the thermodynamics chapter. Okay, so the nice thing about this is a lot of this stuff really just kind of goes back to basic thermodynamics when we think about it. So now, if you work this out, you end up in a situation where you can actually calculate the energy difference if we wanted to do that by just looking at the energy difference between two of these orbits. And this is where we'll end it and maybe do a little bit of practice. So if I had an E sub 2 minus an E sub 1, because an electron could start out at, say, E2 and go down to E1, how would I actually characterize that? Well, I could characterize it in terms of exactly what I've got there. I've got a minus r sub h over n squared for orbit 2, minus the same thing, an r sub h over an n squared for orbit 1. Okay, so then based on that difference, you could calculate the energy difference associated with an electron transitioning from one orbit to the other, say E2 coming back to E1, as I showed you here in the diagram. Okay, so you could actually calculate that difference in energies. And you see this often in terms of the Rydberg constant being pulled out and this sort of thing, but this is basically what it boils down to. All right, so at this point, let's just practice a little bit. And a lot of my practice, I think, just goes back to looking at the difference between the models of frequency and wavelength and that sort of thing, the photon model versus the wave model. Any questions about what I just did here? because this is basically my simple Bohr model, which is the simplest possible model of the atom that we can possibly talk about. Okay, so it's usually where we start. It's what I call the high school model. So when you talk about the model of the atom, like in a general chemistry course in high school, this is kind of where they start you. And then they kind of move you out from there. Now I'm going to sort of give you the deal breaker here right now. The deal breaker, which is kind of moving into the next video that we do, is that this model only works for the hydrogen atom, which means that there's only one electron. As soon as I move to a different atom like helium, which has 2 electrons in it, the model no longer works. Okay, so the long and short of it is we ended up having to actually throw the Bohr model out and develop a new model, which is called the modern quantum mechanical model of the atom, which is kind of the topic of the next video that you guys are going to look at. So let's go back and have a look here at a little bit of practice. And it's only just a few minutes. It's going to work out just about exactly right. So let's go here, light wave model. And while I'm thinking of it, I got to assign the new homework too for this chapter. All right, this is basically just letting you look at the differences between the two models that we talked about here and calculate some frequencies and wavelengths and things like that. Now, these calculations, for example, like in the case of the first one, where they give you a wavelength in nanometers, but notice that the speed of light is in terms of meters per second. First thing you got to do is convert the nanometers to meters, right? So everything always has to agree with the units and the constant, doesn't it?